Hello everyone. Today we're going to ride the edge of the most mysterious monsters in the universe, black holes. Imagine you're drifting silently through space, a lone traveler cocooned in your tiny ship, when suddenly your instruments go haywire. Ahead lies a patch of darkness more complete than night itself. No stars shine there. It looks like a hole torn through the cosmos. Your ship begins to shake. Not from any explosion or sound, but from the whispering tug of warped space. You are about to meet a black hole. Most people think of space as a blank canvas, flat, infinite, reliable. But space is more like a soft stage, one that bends when mass steps on it. A marble placed on a trampoline creates a dip, a place where smaller marbles roll inward. This, in essence, is gravity. Now picture replacing the marble with a lead bowling ball, then a car, then something far more massive. The stage doesn't just bend, it caves in, breaks. That break? That's a black hole. But how could a broken stage trap even time? Could anything fall in and escape again? At the heart of this mystery is how matter distorts reality. When a star with dozens of solar masses dies, its outer layers explode outwards in a supernova, but its core collapses inwards. At nearly a quarter the speed of light, this matter compresses into a point so dense it snaps space-time. You may not know, but a black hole with the mass of 10 suns could fit into a space smaller than a small town, just 60 kilometers wide. How can so much be squeezed so small? What's left when space breaks? You watch as a comet swings past the edge of the darkness, its tail glowing hot, burning at millions of degrees. That's because it isn't just falling into the black hole. It's being shredded, heated by friction as particles smash together at insane speeds. As material spirals inward, it forms an accretion disk, bright enough to outshine whole galaxies. And yet, inside the black hole itself, there's only silence. Why does something that looks like nothing create the brightest lights in the universe? As your ship draws closer, light itself begins to behave strangely. Around you is the photon sphere, a region where light can orbit the black hole. You stare forward and inexplicably see the back of your own head. Time slows, space warps. If you turned around, you'd see your future arriving before your eyes. What would you do if you could watch your own time crawl while the universe above spins on without you? And here's the real twist. Time isn't just slower near a black hole, it's broken. For the people watching you from far away, you seem frozen, suspended just above the event horizon. From your view, the universe above fast forwards into distant future centuries. It's like falling into a one-way time machine, traveling forward without a return ticket. What if your journey meant leaving behind everyone and everything you ever knew? But it gets more grotesque. If you continue forward, your body stretches like dough. This isn't a metaphor. It's called spaghettification. Your feet feel a stronger gravitational pull than your head, pulling you apart atom by atom. It's an exquisite, painful symmetry. Gravity both preserves the cosmos and tears you to threads. So the question becomes, would you rather burn into light outside, or be torn apart inch by inch inside? Still, not all black holes are equally merciless. Supermassive ones, the kind lurking in galactic centers, are gentler giants. Their event horizons are so far from their centers that the gravitational gradient is weaker. You might fall through intact, drifting deeper without being instantly shredded. But does that mean you're safer? Or just doomed more slowly? Falling. That's all you know now. The engines are dead. Your controls meaningless. Gravity has taken command, and there is no going back. From outside, observers would swear you never crossed the threshold. They'd see your ship grow redder and dimmer, fading like a ghost into the horizon. But inside, to you, time feels normal, more or less. What is not normal is the scenery, because soon enough, it disappears. The event horizon isn't just the border of no return. It's where physics, as we know it, stops making sense. You look around, but light itself can't make it to your eyes from many directions. Your entire universe shrinks to a single point of light far above. The blackness below is total, hungry, rising. And you, absurdly, are falling toward the singularity. Something no one, not even Einstein, could quite understand. What do you think lies at the end of everything? As you fall deeper, space curves so hard that every direction points inward. There is no away. Every push you make only drags you faster to the center. It's like rowing toward a waterfall, where the water falls not downward, but in all directions. There are still people arguing about this, by the way, whether space itself flows into the singularity, or whether time simply breaks down. But either way, you are being carried. What if every path only led to one place? You try to stay still, knowing that effort only hastens your end. But even doing nothing doesn't help. The singularity is waiting, an invisible needle where all roads end. It is not a surface or a place, it's an idea, one where matter becomes infinitely dense and space folds into nothingness. What does it mean for a person to be reduced to that? Does something of you survive? Strangely, as your atoms come apart, they lose their identity. The black hole doesn't remember who or what you were. Your mass joins its total, but your name, your memories, your story, erased. This is called the no-hair theorem. A black hole has no features beyond mass, spin, and electric charge. Your childhood dog? Gone. Your favorite song? Vaporized. Does this mean that identity is just a temporary arrangement of particles? Here, your atoms join countless others. Asteroids, stars, astronauts, crushed into sameness. The singularity doesn't care. It accepts all with equal indifference. And like fundamental particles, black holes are identical at the core. Each one a clone, defined only by its few external traits. But are they really all the same? Or is there a hidden difference we'll never see? But now let's rewind slightly. Because most black holes aren't static. They spin, and spin changes everything. Rotating black holes don't just warp space, they drag it. Like a cosmic blender, they create a whirlpool where space and time swirl together. Around them forms the ergosphere, a region where standing still is impossible. Everything is pulled along, like leaves caught in a river current. What happens when space itself becomes a force? In this storm, a strange opportunity arises. If you were clever and very lucky, you could, in theory, extract energy from the spin. It's been proposed as a kind of black hole power plant, using the Penrose process. If a particle enters the ergosphere and splits in two, one piece falls in, while the other escapes with more energy than it had before. So even this monster has its loopholes. Could the universe's deadliest object also be its most powerful battery? Even stranger, the spinning singularity may not be a point. It might be a ringularity, where the laws break differently. Some physicists speculate that just maybe this could be a bridge, a wormhole, a doorway to somewhere, or somewhen else. But we have no proof, only math. And math can lie when stretched too far. Would you risk everything for a chance at a doorway to another world? Now we reach the real paradox. Inside the spinning black hole, time loops. The equations say time travel might be possible here. If someone could navigate the internal chaos and avoid the crushing singularity, they might emerge elsewhere, or else when. But it's a big if. And even if true, escaping the black hole's grasp seems impossible. What good is a time machine if you're stuck inside forever? And yet, this possibility haunts scientists. If information can't escape, then how can physics remain consistent? The information paradox, raised by Stephen Hawking, suggests that if things fall in and are lost forever, the the universe breaks its own rules. Because quantum mechanics says information can't be destroyed. This conflict is still unresolved. Which side would you take? Hawking's firewalls or a quantum rewrite of reality? Let's end this fall where all falls end, at the singularity. Whatever it is, wherever it leads, it is not part of our universe anymore. It is the end of your path, the conclusion of your identity. And still, somewhere above, the tiny point of light that was once your universe shines. A reminder that even as everything ends, far above the abyss where you vanished, the universe continues. Stars are still born and die, galaxies still dance in gravitational embrace, and black holes still reign as cosmic monarchs of doom. But even these monsters are not eternal. Though their lifetimes are almost inconceivably long, they are slowly, subtly evaporating. At the edge of their dark hearts, something begins to leak. You might think a black hole is the ultimate vault. Nothing escapes it, not even light. But quantum physics disagrees. At the very edge of the event horizon, the vacuum of space is anything but empty. It's teeming with quantum jitters, tiny fluctuations that constantly pop pairs of particles into existence. One matter, one antimatter. Usually, they annihilate each other instantly. But if this happens just right, one particle can fall into the black hole, while the other escapes. That escaping particle is Hawking radiation, and so black holes begin to bleed. What happens when the strongest thing in the universe starts to die? Hawking radiation is not stolen from within. It's new, but its cost is real. The black hole loses mass. Slowly at first. A black hole with the mass of our sun would take 10⁻⁶7 years to vanish. That's a number so big it feels meaningless. But imagine, every grain of sand on every beach on Earth, multiplied by 1 billion. And for each of those grains, 10 billion years pass. You still haven't come close to that time span. Can we even imagine such a future? As time grinds on, stars grow cold and stop shining. The universe enters its dark era. Black holes, now the last active things, are the only remaining engines of change. But even they decay, and the more they lose mass, the faster they radiate. A shrinking black hole becomes hotter, brighter, until, in its final moment, it explodes in a flash of energy, and then, nothing. What kind of end is it when not even the darkness remains? But here's the cruel twist. We'll likely never witness this. These black holes will outlive everything, stars, planets, even atoms. The last one might evaporate in a universe that's billions of times older than our current one. And when it does, there won't be anyone left to see it. Do we leave behind legacies in a universe destined to forget them? Still, the existence of Hawking radiation presents a challenge. If information disappears inside black holes and their remains vanish without a trace, then something vital is lost. This breaks the laws of quantum physics, which insist information must be conserved. This problem, the black hole information paradox, is still unsolved. There are theories. Some suggest the information is smeared across the event horizon. Others believe it leaks out through radiation in bizarrely scrambled form. Or maybe, just maybe, the entire universe is a hologram, and nothing really falls in at all. Can you trust your instincts in a universe that might be an illusion? This debate has reached absurd levels. Some physicists argue for the existence of firewalls, walls of searing energy at the event horizon that incinerate anything falling in, thus preserving information by violent means. Others claim space-time must be rewritten entirely. There are still people arguing about the very nature of reality, and black holes are at the heart of it. What do you believe? That the universe is logical, or that it's stranger than we'll ever know? One famous physicist, Leonard Susskind, took Hawking to task on this issue. Their debate became legendary, spanning decades, blackboards, and billions of calculations. Eventually, Hawking conceded, maybe information isn't lost, but the question remains, how do we retrieve it? And if we can't, what does it mean to know anything? There's one more thing. Everything we've talked about, falling in, spaghettification, singularities, assumes non-rotating black holes. These are mathematical conveniences, not real objects. Every black hole that's ever formed from a star's death should be spinning. Fast. Some spin at over 90% the speed of light. This makes their inner geometry even weirder. The singularity isn't a dot. It's a spinning ring. A ringularity. It might have tunnels through space-time, but could we ever send a signal through? Or would anything sent simply be lost, like tears in cosmic rain? As black holes twist space around them, they create ergospheres where reality itself is pulled into rotation. There's no stopping, no stillness, no escape. Not unless you're clever with physics beyond anything humans have built yet. Could an advanced civilization one day harness this energy? Or even build machines to escape into alternate universes? And then the quiet. With the final black holes gone, the universe enters heat death. A state of maximum entropy. No energy differences, no structure, no events. All that's left is cold, slow decay. Maybe protons decay over trillions of years. Maybe they don't. But there's no one left to check. Is this truly the end? Or a beginning we cannot yet grasp? In the silence of this far future, the legacy of black holes lingers. They were the universe's sculptors, carving galaxies, shaping stars, deciding fates. And though they die, their echo remains in every photon, every wave of gravity, every unresolved mystery. Perhaps the greatest question they leave behind is not, what are black holes, but what are we to wonder at them? We'll never stop exploring. Black holes remind us that the universe is not tame. It is wild and dangerous and magnificent. We peer into their depths and see both our doom and our future, our insignificance and our brilliance. So let's keep asking, keep searching, for in the darkness of a black hole, we glimpse the light of curiosity itself. Now that our journey has concluded, let's pause to breathe in the sheer scale of what we've explored. Black holes are not just objects in the universe. They are the universe's deep breaths, its pauses, its unspeakable sentences. They bend the very canvas on which reality is painted. And yet, even as they devour light and memory, they illuminate the corners of physics we've yet to understand. These aren't just ideas for textbooks or theories trapped in math. They're real. Somewhere out there right now, stars are dying. Matter is collapsing. Black holes are forming, eating, growing, and eventually shrinking, evaporating, disappearing. We may never truly understand what lies beyond the event horizon or whether singularities are real. We might never solve the information paradox. But the mystery, the pursuit, the awe, that's what makes us human. And maybe, in some far-off corner of time, someone or something will decode these secrets. Until then, black holes will remain the great riddles of the cosmos. They are the universe's silence. And into that silence, we listen.